Welcome to this tutorial. Believe you are doing well. Today we are looking at the topic number 38 of our physics curriculum, which is basically the topic X-rays. And I shall be your tutor, Dave Joseph Adeli. And before we begin, we shall have a quick word of prayer. Father Lord in heaven, we invite you in this session. You being the greatest physicist, teach us X-rays. Jesus, I may pray. Amen. Basically, this being our second tutorial, we are still going to tie ourselves to specific objectives because it's basically like our Bible. It's what guides us in be able to know how much we have learned and how much we need to know. So basically, by the end of this topic, we should be able to explain the production of X-rays, of which we covered in the previous tutorial. Also state the properties of X-rays, which we also did. Now, what you need to also learn now is state the dangers of X-rays, explain the uses of X-rays, and finally solve numerical problems involving X-rays. In this tutorial, just to give you an upper hand, we are going to deal with the last one, which is solving numerical problems involving X-rays. Then the next tutorial, we shall be able to look at dangers of X-rays and also explain the uses of X-rays. So basically, let's dive into what is required of us. So first of all, we are going to figure out that X-rays is a part of the electromagnetic spectrum. This from the topic electromagnetic spectrum is well explained there. So basically, X-ray is part of that. So when we speak about electromagnetic spectrum, we need to find ourselves, we need to explain to ourselves what is electromagnetic spectrum. So this electromagnetic spectrum is basically a collection of electromagnetic waves of varying wavelengths and frequencies. So that's basically what it is. So examples of those electromagnetic waves, they include visible light waves, we have radio waves, we have X-rays, ultraviolet, we have infrared and gamma rays. Basically, those are what we have as electromagnetic waves. And basically, from the topic waves 1, we are able to see that electromagnetic waves, these are a special type of waves that don't require a material medium to be able to traverse through. They don't require a material medium, they just pass through any particular medium. That's basically one of the properties that we need to remember. So if I just bring you to this chart, it gives us an upper hand of what X-rays, of where X-rays are found. So this is the chart of an electromagnetic spectrum. So we have here radio waves, we have microwaves here, we have infrared, we have visible light, we have ultraviolet rays, we have X-rays, and then finally gamma rays. So maybe just to bring up this notion, to be able to understand this, because in an examination setup, you shall be asked, for example, name at this particular slot which particular wave is here. You have to know the order, in fact, and how they behave in terms of their wavelengths and their frequencies. Basically, you can come up with an acronym, RAMIVU XG. RAMIVU. Basically, that A should be small, but if you remember, it will be good. RAMIVU. And then this one comes X and G. So Ra is radio waves, M is microwaves, I is infrared, V visible light, U ultraviolet rays, X-rays, G gamma rays. And how do they behave? The frequency increases in that particular order. From radio waves to gamma rays, it increases, meaning gamma rays has the highest frequency. And in the reverse order, from waves 1, we saw that V is equals to F lambda. So basically, frequency and lambda are inversely proportional. So across this list, there's a decrease of wavelength. I believe you can even see it from this chart. The wavelength keeps on reducing. In the meantime, the frequency also increases. That's something you need also to note. And basically, as you increase in your content, you shall also be able to understand how the particular figures come about. So basically, let's just dive a little bit in electromagnetic waves as we continue in this topic of X-rays. So basically, electromagnetic waves are transverse waves which result from oscillating electric and magnetic fields at right angles to each other. Now let me begin from what you know. From your textbook, you shall have this image of which we have two waves that are perpendicular to each other. So we have this, the first axis pointing upwards, we have the electric field, and then perpendicular to it we have a magnetic field. So basically these are two of them, so they are at right angles to each other. I believe you can notice that. So they are at right angles. That's something you need to note. Now to make it more clear, and you can see even the direction of the wave, to make it more clear, let me give you another image of it so that you maybe appreciate it more better. So the blue is basically the magnetic field and the red is basically the electric field. And this one even gives you a clearer view. We find that they are at perpendicular. Each of these is mutually at right angles. So that clearly explains what it is and the key is here. So basically, if you find a challenge, you can pause the video or rewind to the specific point you find it a challenge to be able to go back there. So let's go back to X-rays as a part of electromagnetic spectrum. Find that experimental results of polarization of X-rays and diffraction on X-rays by crystals have confirmed the wave nature of X-rays. Notice that when we are beginning the topic, we said this special type of waves are called X-rays because the one who realized it, that's Rontgen, when he was performing cathode rays experiment, he accidentally came to particular type of rays which he cannot be able to describe. So he just gave them the term X because he never knew its nature. But with the time, with the various experiments, one of them being polarization and diffraction, some ways or some natures have been able to be found out. And the main nature that we find here is basically with respect to its wavelength. So through diffraction experiment, the wavelength of the X-rays have been confirmed. Something we need to note. So just a moment, there's a vehicle passing nearby. There shall be quite some noise, but I believe we can be able to continue together. So basically, we realize that diffraction is basically when a wave moves around an obstacle. And if it moves around an obstacle, there shall be an effect on how that particular wave shall move around that obstacle. That's something you need to appreciate much. So from the topic we've studied, this one needs to be well understood. If it's a challenge, you can be able to see, you can be able to get some special attention later to be able to find out how to be able to explain that. So diffraction in this case, the wave, or let me say now in this case the electromagnetic wave, when it goes around the obstacle, with respect to the wavelength, it shall diffract or not diffract. So if the wavelength is greater than the aperture that is going through the obstacle, it shall be able to diffract. But if it's less than the aperture, it shall not diffract, it shall go undiffracted. That's an example very I've just thought of this. If they ask you also why don't the sun rays diffract, it's because they have a very small wavelength that it can be able to diffract. So that's basically just an oversight to be able to give you an overhand. So X-rays are electromagnetic waves of very short wavelength of order 10⁻⁻10 meters. Now for classification purposes, electromagnetic waves in the appropriate range of 10⁻⁻11 to 10⁻⁻8 meters are considered as X-rays. You can appreciate that much from the electromagnetic spectrum, and you can be able to see the way they have been arranged in terms of their wavelengths and be able to appreciate that much better. So this range overlaps with the ultraviolet at the upper end and gamma rays to the lower end. The only difference being only in the manner of production of each. Let's see what I simply mean in this case. Notice X-rays are here. It overlaps the ultraviolet and also overlaps the gamma rays. There's an overlap, but the X-rays are basically there. So it overlaps the ultraviolet rays to the upper end, and the lower end, the gamma rays. So that's what we have as X-rays. Let us just dwell now into energy of X-rays, whereby now we'll have to test our mathematical skills in terms of this in terms of this subtopic. One, in a bombarding electron is stopped in a collision, most of its energy is usually converted to heat energy. This one was well explained when I was talking about production of X-rays. So at a given accelerating potential difference, the X-rays produced will have varying wavelengths, with the shortest wavelength corresponding to a collision in which all the energy is assumed to have converted to X-rays. So that is the first case I want you to note. And then the kinetic energy of the bombarding electron is practically equal to the electron volt, EV. That EV basically here is simply the electron volt. We shall appreciate much when it comes to the point of calculation, and is given by this particular formula. Kinetic energy is equals to electron volt, where E is the electron charge. In terms of Coulomb, this is specific, it's a unit that was already determined. It's usually 1.6 by 10 power negative. That's basically the number that we'll have. We'll appreciate it much when it comes to the values, whereby V is the accelerating potential difference. So when all kinetic energy of an electron is used to produce the energy of X-rays, the frequency of the X-rays will be maximum. Notice frequency is usually inverse proportional to wavelength. When wavelength is minimal, frequency is maximum. That's something you need also to note. So using Planck's theory, the energy of X-rays is given by E is equals to HF, whereby H is the Planck's constant and F the frequency of radiation. Believe you can now start linking up things. How do you calculate energy? How do you calculate this? And be able to see how it happens. So this is basically one of the theories that Planck came up with on how to calculate the energy of X-rays. So the value of this Planck's constant is basically 6.63 by 10 power negative 34 joules second. There is no way you'll be able to get that until you get for further learning on how he was able to derive that, but it's a constant. So there are values that you need to know they are constants, but not basically cramming them, but understanding how they come about. So thus, the electron volt will be equal to HF max. Now notice, kinetic energy, which is basically still energy, was equals to electron volt. And we find that kinetic energy is also equal to HF. And the same kinetic energy is what is written here as E is equal to HF. So basically, electron volt will be equal to the same formula. So since the speed of light, C, the velocity of light, is frequency, the product of frequency and wavelength, therefore we'll be right to say then the maximum frequency is equals to will be basically the dividend, or not dividend, the quotient of velocity of light and the wavelength, the minimum wavelength. Basically, this in the topic photoelectric effect shall be well clearly explained by something known as work function. So the electron volt, therefore it will be right to say it is equals to the Planck's constant multiplied by velocity of light divided by wavelength. What have we simply done? We have substituted frequency here with this formula. So basically we're just playing around with the formula. So this shows that most energetic X-rays have shortest wavelength. So most of them, if it has a high energy, it has the least wavelength. These are some of the points you need to note when we shall come to the next tutorial, when we'll be speaking of hard X-rays and soft X-rays. Let us dwell into an example so that we're able to appreciate much of what we have been saying. So please, you may pause the video if you not mind, so that you may try working on this with the basic formulas that you have and the constants that the question has provided. Now I believe what you have been able to come about is the answer that you have. Let us just work out with you so that you will be confident. So the solution: find the frequency of energy of X-rays whose wavelength is 10 by 10 whereby negative 10 meters in a vacuum, whereby the velocity of light is 3.0 by 10 power 8 meters per second. Planck's constant is 6.63 by 10 power negative 4 joules second. So basically, we are looking for frequency and energy. Frequency is found in the formula of the speed of light is equals to product of wavelength and frequency. That basically tells us that frequency is equals to the speed of light divided by wavelength, whereby you'll get your frequency as 3.0 by 10 power 18 hertz. Energy is equals to hf from Planck's equation. So if I substitute whatever I have there now, I'll find that energy will be equal to 6.63 by 10 power negative 4 joules second multiplied by 3.0 by 10 power 18 inverse of second. Now I need to explain what I've simply done here. Notice when you are looking for frequency, meters and meters will cancel out, so it will remain with 3.0 power 18 per second, this formula here. So it's the same as saying hertz or frequency. So I've simply put it here so that you may have something known as dimension analysis. In one of the tutorials coming up next, you shall be able to understand what dimension analysis is when we shall be looking at how to answer physics questions. So basically, this seconds and that second cancels out. It means 1.989 by 10 power negative 15 joules, which is basically the energy that we have. So the answers here will be frequency is 3.0 by 10 power 18 hertz, and energy will be 1.989 by 10 power negative 15 joules. Second example. May pause the video if you don't mind to be able to work that out. Now, beginning with the first question, the frequency of X-rays range from 3.0 by 10 power 17 to 3.0 by 10 power 19 hertz. Determine 1, the range of wavelengths, number 2, maximum energy of X-rays, and you have the various constants there. Let's begin out. First solution. We'll basically find that we have two frequencies, meaning because we are looking for the range of wavelengths, we'll also have two wavelengths that we're calculating. So let the first wavelength be lambda 1 and lambda 2. So the speed of light will be equal to that formula, and if I punch everything correctly, we'll figure out that the first frequency will be 1.0 by 10 power negative 9 meters. Also, the second wavelength will be in the same formula. Second wavelength will simply be 1.0 by 10 power negative 11 meters. So it will be right to say the range of wavelengths is 10 power negative 9 meters to 10 power negative 11 meters. That is that will be the range of wavelengths. The range of wavelengths of that particular X-rays that you have. Second part of the question, we will look for the maximum energy of the X-rays. Now we need to be careful. Maximum energy, E is equals to HF. How do you get maximum energy? How are they related? Notice that E is directly proportional to frequency. So it means for maximum energy, I'll have to use maximum frequency. So basically, with my formula, E max will be equal to that. So because they're directly proportional, my frequency will be the highest frequency, which is 3.0 by 10 power negative power 19 hertz. And if I substitute everything correctly, I'll have 1.989 by 10 power negative 11 joules, which is basically the highest energy or the maximum energy in this case. Example 3, if you don't mind, you may pause the video to be able to work that out. We have been asked, an X-ray tube has an accelerating potential difference of 100 kilovolts. Now, not 100 kilovolts. So in your numerical data, you will have 100 kilo. Kilo is basically 10 power 3. So basically the total everything will be 1 times 10 power negative 5, power 5, not negative, power 5 volts. Determine the shortest wavelength in its X-ray beam wavelength. So basically the first formula in our solution will be electron volts is equals to HF max, which is equals to H divided by C which is the speed of light divided by minimum wavelength. So if you substitute everything correctly with this particular formula, you'll end up with the wavelength being 1.0 by 10 power negative 11 meters, which is basically the wavelength of that specific wave. So with that's what we got, and basically success in your preparations. May God bless you abundantly. Meet you in the next tutorial, which are going to look at the last two sections of this topic before we call it off.